Welcome to this lecture. In the last lecture, we had discussed about the interaction diagrams. We said that there are two main types of interaction diagrams, the sequence diagram and the collaboration diagram. The sequence diagram captures how the objects interact during execution of a use case, and we also said that the sequence diagram plays a very important role in a design process. Any design process, sequence diagram has a very important role. The role is that it helps in identifying which classes have which methods, that we call as method population in the classes. To start with the design process, we identify the classes that exist, and later we identify the methods, and then we identify the attributes. So, the sequence diagram has a very important role of identifying which classes should support which methods, and then we saw the collaboration diagram as automatically derivable from a sequence diagram, and most case tools they just display the collaboration diagram based on just a press of a button. The main purpose of the collaboration diagram is that it shows the association relation between different classes. Now, we know that based on the sequence diagram, we can also write the code for a method, because we know that when the method is invoked on a class, what it needs to do. It might call a self method or call another method with some argument, etc., and therefore, some code also gets developed for different classes. Not only that, the method prototypes are developed for every class, but also the method code gets developed, skeleton code. Now, let us do it through a small exercise, and that is simple enough. Given a diagram, we would be able to develop the code, because it is very simple. Let us see that. Let us see that we have this sequence diagram. There are three objects which participate in this sequence diagram. Method M1 is first invoked on the object A, the class capital A, and then it invokes the create. Okay, I should have put the stereotype here, which I can put now. Just put the stereotypes here to be correct. It invokes the create on the B class, and the object, anonymous object, gets created here, and then it calls the do A method on the B class, the anonymous object of the B class, with argument this, and remember this is the small a itself, and then it returns a flag, and in turn the object of the B class, it creates an object of C class called as C. The name of the object that is created is C, and then it calls the do B method of the A class with the argument C. So, what will be the methods for different classes, and can we write some of the code here? We know that M1 is a method of A class, do A is a method of the B class, of course create, okay, that is the constructor for the C class. Now, the question is that can we write the code for class B? So, that is for do A method. So, we know that class B contains do A method. It takes an object of class A as argument, and then inside the method it will create a class C. So, it will call the new operator in Java for the class C and then call Doubly method of the class A. So, if we write the code neatly, we will have class B and then it has the do a method, it returns a flag integer and then first it creates a C object and the name of the object created is small c, and it calls the A object, the Doubly method of the A object with C as the parameter and then it returns a flag. So, not only that, based on the sequence diagram we can populate the methods, but some skeletal code for the different methods can also be created. Now, let us look at the state machine diagram. This is also an important diagram, even though it is not developed for every class in every problem, but then if the classes do have significant states, then we show that in the form of a state machine, and also the state machine helps to generate some code, because our idea is that once we do the design we should have some code written for us. Most case tools do that, good case tools generate lot of code and we just need to fill few of the code there. And we saw that how the interaction diagrams help us to generate the code. Now, let us look at the state machine diagram and see that if the classes, some classes have significant states, then we can develop the state machine diagram and at the same time the code for that class will get generated. We will see the nitty-gritty of the state machine the state machine diagram, and also see the code that a state machine diagram can generate. The state machine diagram, as it is called in UML 2.0, is based on the state chart diagram. The state chart diagram is a refinement of the finite state machine. We all know the finite state machine, and the state chart diagram was proposed by David Harrell long back, maybe 30 years back, to handle two problems of the finite state machine. Even though we use finite state machine for small problems, but if we use it in object orientation, in modeling classes, systems and so on, and in many other applications, it suffers from two main problems. The FSM suffers from two main problems. One is called as the state explosion, that is the number of states becomes too many, hundreds, thousands, and it becomes very difficult to draw the diagram on a page or on a screen and also to understand the diagram. The second problem is that the state machine is just a sequential diagram, states get activated one after other. We do not have concurrent states, and the state chart diagram overcomes these two basic problems of the FSM, and we will see that it is an elegant formalism, and UML uses the state chart diagram and calls it as the state machine diagram. The main improvements to the finite state machine is hierarchical state. A finite state machine is a flat state machine. If we draw an FSM, let us say we draw it like this, that we have two states and then there are some transitions. It is a flat state machine, let us say state S1, S2, and then some transition based on some event, some transition takes place, and we have some action E1 causes this transition, E2 causes this transition. But in a state chart diagram, we have hierarchical states, that is, the state here can have further states. So, even though at the top level we have this state machine, but we can look at any state and that also contains a state machine, and this may contain state machine. So, there is a hierarchy, and if we look at this state in the second level, it might also contain a state machine. And this is the one mechanism, hierarchical state, to handle the problem of state explosion. Earlier, as the number of state variable increased, the state FSM became extremely complex. Number of states increased exponentially with the number of state variables. We will just see that with an example, that how the states increase exponentially with state variable. But here we address the problem of state explosion by having a very simple diagram with few number of states and transition, but then we use the abstraction mechanism. We said beginning of our discussion on software engineering that wherever things become very complex, we use either abstraction or decomposition to handle that, and here we use the abstraction mechanism, and that is done through a hierarchical state model. So, instead of making the diagram flat and very complex, we have a hierarchical diagram, and the top level is simple and the complexity are slowly added over the hierarchies. And here, for representing the concurrency, we have composite state, that is, within one state we can have a concurrency, that is, the object can exist in two different states within one state. Let us we will look at that. Let us first look at an example and understand the state explosion problem in a FSM. Let us look at this robo, and this robo can make movements. The first state variable, let us try to compute the number of states in modeling a robo's behavior. Let us assume that there is a switch to have the movement of the robo on or off. The robo can move if the movement is on, movement can be off also. So, there is the state can be that movement on and movement off. Now, there is another state variable called as direction, and the direction can be forward, backward, left and right. So, this state variable direction can take 4 different values, and these are 4 states. So, based on these two, we will see that the state for movement there are only 2 states, that is the robo movement on, robo movement off. But now, with the second state variable, we have 8 states, that is robo movement on with direction forward, robo movement on with direction backward, robo movement on with direction left, robo movement on with direction right, and similarly robo movement off with forward, backward, etc. So, with these 2 state variables we have 8 states. Now, there can be further states. For example, the left hand raised or down. So, these are 2 states. Now, the number of state variable becomes 2 into 4 into 2, because for each one here, each state here, we can have 2 cases, left hand raised or down. Similarly, the right hand raised or down. Similarly, we will have head straight or turned left or turned right. We can have the headlight turned on and off, and we can have the turn left, right or straight. So, it may be proceeding straight or it may be turning to left or right. So, to model this robo, how many states we need in a simple finite state machine model? We will need 2, that is 2 into 4 into 2 into 2 into 3 into 2 into 3. So, this becomes 8, 16, 32, 96, 192, and this becomes 384. So, just imagine FSM you will draw to model this, and it has 382 states. If you even if you spend a month trying to understand the behavior, it becomes very complex. But using the state chart notation, we can draw a very simple diagram to represent these the state machine for the robo, because we will use the concurrent states and the number of states will drastically come down to only a few. Now, let us look at the features of the state chart. So, this is the concurrent state machine. For the robo, we have one thing is that movement on and off, and at the same time we can also set the movement to forward and backward. Similarly, we can set the state to left hand raised, left hand down, and so on. Just see that the state machines are becoming independent and therefore, the combinational explosion that was occurring there is stopped here in the state chart, because these are independent. The state variables are shown in the concurrent state, that is at the same time it can have the state change occurring from forward to backward and on to off and so on. The other one is the hierarchy is the nested states. The state S1 contains another state machine S2 and so on. And of course, there are few other features on a state chart like history state, broadcast message, actions on state entry, state exit, etc. This part we will not discuss in this lecture. So, to draw a state chart diagram, we draw an initial state which is a filled circle. We will draw an initial state. To start with, it will come to this state. Let us write S1, and then so by default to start with it will start in S1, maybe go to S2 based on some event E2, and there is a final state which is a filled circle inside another circle. Is a rectangle with rounded corners. These are the state representation, and arrows between states, these are the transition, and we can have Boolean logic here to show that based on some condition the transition occurs, even if the event E2 occurs, the transition will not occur unless the condition holds true. Now, let us address this question, that if we develop the state machine representation, let us first look an FSM and we can do for state chart, that given an FSM, how can code be generated from that? Because an FSM or a state chart is used to represent the state model of a class. Now, can we generate some code for the class? Actually, it is very simple if we understand it. Let us look at that. There are three main approaches. One is called as doubly nested switch in loop. So, the meaning of this is that we have one switch in C, and inside switch we have, let us say, case 1, and inside that we have another switch event, and then we have E1, E2, etc. And similarly, case 2, that will also have a switch. So, there is a doubly nested switch. So, there is a switch here inside another switch, many switches here between nested switches, and then this is within a loop while some condition. We will get a code like this. This is the first approach. We will see that it is extremely simple. Given FSM, we can easily draw this, develop this code. We can actually automatically generate this code. The second one is a state table. This is also straightforward. We just use a table and write the states, and for each S1, S2, S3, and based on the different events, if it is in some state what occurs, etc., we can also write that. This is very simple, we will discuss that, but the state design pattern we will not be discussing in this lecture. So, there are three principal ways: the doubly nested switch in a loop. Here we use a global variable to store the state, and we switch on the state, and the event type is the discriminator in the second level switch. But here it is bit harder to handle concurrent states, composite state, history, etc. And the state table is a straightforward table lookup. In the design pattern, state design pattern, we have as many classes as the states, and the transitions are methods in the class. We will not be discussing this. First, let us see the doubly nested switch approach. Here we have the states as the global variables. The states as the global variables here, and then we switch on the state. This is a loop here. We keep on doing this, and as an event occurs, first switch on the state. Depends on which state, the same event may have different actions. If it is in state 1, again we switch on the event here, and depending on the event 2, let us say we do something, that state becomes, the current state becomes state 3, and printf something and break. And if the event 2 occurs when it is in state 2, maybe we have state becomes event 2, maybe state becomes state 1, get some input from the user, do something, and then break. So, this is a simple translation. We will just look at the state machine, and we see the state variable that is used. We write that here, the form of the specific type of the state, whether it is an integer and so on, and then we look at the events here E1, E2, E3, and we look at the states S1, S2, S3, and then switch state case S1. If the event E1 occurs, then transit to S2, and this is a simple state machine, and that is it. And if it is in S2, it only switches based on E2, and there the state is set to S3, and in S3 it transits to S1. So, this is a very simple code, and the the state table is also very simple. We can also look at that. So, here this is a doubly nested switch. The first one is switch on the state, the second one is switch on event, and depending on the state, the same event may have different actions. The state table approach is also extremely straightforward. Here we have the present state and the events that are recognized here, and then what action takes place. So, which will be the next state? If light is off is the present state and it reacts to E1 and E2. If E1 occurs, then light is off. So, there is no action basically for E1. If E2, then light becomes on and set the red light flashing. Similarly, for every state we write the specific events and then what are the state change and what are the action. So, it becomes easy to write the program whenever there is it is in a state, we just look up on the state table and set the state next state based on this, and then we perform the action, and that is it. The code becomes very straightforward. So, we are almost at the end of this lecture.